Hey everyone, welcome back to Calculus 2. This will be the fourth lecture of the course, and in this lecture we're going to discuss the fundamental theorem of calculus. And so this is a very this is a favorite section of mine, not only because the fundamental theorem of calculus really knits so much together so elegantly, but also because the proofs of the fundamental theorem of calculus are very easy to understand and very nice to. They have a beauty to them. So with that, let's go ahead and get started. And so we'll call this section 1.4 the fundamental theorem of calculus. Okay, and so up to this point we've talked about kind of the two major branches of calculus. So we have the differential calculus, and that's the one with, that we mostly occupy ourselves with for calculus 1. And we have the integral calculus, and that's the one that we're kind of venturing into now. So these are the two major branches of calculus, and you can kind of think of them each as having their own sort of fundamental problems, right? So in the differential calculus, the fundamental problem is the tangent line problem. There's other things too, but that's kind of one of the main motivators there. And then in this one, the integral calculus, the fundamental problem, you might be able to say, is the area problem. Okay, so being able to find the area under a curve, above the x-axis. So the fundamental theorem of calculus, as we'll see in a moment, is the bridge between these seemingly distinct concepts. Okay, so let's go ahead and jump into it. So this is the fundamental theorem of calculus. So let f be a continuous function on the closed interval a, b. Okay, so f is a continuous function on a, b, and let big F be an antiderivative of little f. Okay, then here's what we have. The definite integral from a to b of f of x is equal to big F of b minus big F of a. Okay, so previously we have talked about indefinite integrals, and we understand the concept now that an indefinite integral, the solution to an indefinite integral, is a family of functions that are, that all have the form of the general form of the antiderivative of whatever little f happens to be. And then we've also been talking about definite integrals, and with definite integrals we've said when we evaluate a definite integral, what we get is a number. So we don't get a family of functions, we get a number. This is kind of the connection between all of those things. Now additionally, one of the central ideas here is that differentiation and definite integration, right? Differentiation, these are antiderivatives, and definite integration are inverse operations of one another. So let's explore that just briefly, and then we'll prove this theorem. Okay, so when we talk about the tangent line problem, maybe we have a curve like this, and the tangent line problem is, if you recall from Calc 1, it's the problem of identifying a line that touches said curve in exactly one place. And the slope of that line we talked about could be identified as by identifying the derivative, or sorry, the change in y and the change in x, and the slope there is the ratio of the two, dy over dx, rise over run. So we kind of know, we've kind of seen this before. Now when we come to the definite integral, let's say we have another function, and what we're interested in is the area, right? So maybe there's an x-axis here, and you've got some interval, and what we do with definite integrals is we generate some sort of rectangle, right? Using whatever method, either lower sums, upper sums, Riemann sums, whatever the case may be. And from that, we derive a width, which we denote as delta x, and we derive a height, which we denote as delta y. And then the area here is the product of the two. Okay. And so, interestingly enough, these delta y, delta x's have this inverse relationship, right? So over here you're doing division, essentially, and over here you're doing multiplication, right? So it's just a window into the inverse nature of these two fundamental problems. Okay, and so I mean, just like how multiplication and division are inverses of one another, it does turn out to be the case that integration and differentiation are inverses as well. Okay, so that's just kind of an introduction. Now let's prove the fundamental theorem of calculus quick, and then let's do some examples. And I think the proof is great. I like the proof a lot. It's one of those proofs that are really easy to follow, very intuitive, I think. And then once we get into the examples, I think people they'll probably be kind of a eureka moment for many people. Okay, so let's prove this. So remember, we're trying to prove, we wish to show that a to b integral of f of x dx is equal to big F of b minus big F of a. So basically that this derivative can be evaluated by finding an antiderivative and just identifying the difference between the antiderivative at b and the antiderivative at a. So kind of remarkable. So let's prove this. So we're going to start with a partition of AB. So let delta be a partition of the closed interval AB for which we're operating on. Okay, and so we can write that out more explicitly. We'll say A is equal to x0, which is less than x1, which is less than x2, dot, 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 less than xn, which is equal to b. Okay, so that's the partition delta. Now, of course, since there's integrals involved, we're going to end up, we're going to end up taking the limit as the norm of this partition goes to 0, but we're not there yet. So we're just going to start by just writing it out and know that we're dealing with a partition. Now, it's also true that if you take the antiderivative fb evaluated at b minus the antiderivative evaluated at a, well, we know that b is x of n and a is x of 0, so we can expand this, right? So we could write it like this. This is f of x of n minus f of x 0. Okay. Now we can write this even in an even more expansive form. We can write f of x of n minus f of x of n minus 1 plus f of x of n minus 1 minus f of x of n minus 2 plus f of x of n minus 2, and so on until we get down to f of x1 plus f of x1, so minus f of x1 plus f of x1, and then finally the last term would be minus f of x0. Now, what have we done here? Well, each of these pieces we're just subtracting and adding the same term each time, right? So all this stuff in the middle is just really like algebraic trickery. And really what's important is this in term and this f of x of n and this f of x of 0. Those are still in place, and there's all this stuff in the middle that just kind of is a little bit of an algebraic trick. Okay, and so this could all be written as the sum from I equals 1 up to n of f of x I minus f of x I minus 1. Okay, so that's all. That captures everything, right? So if I is equal to 1, this is f of x1 minus f of x0. So it's this guy minus this guy. Okay, remember this is a plus here. And then if x is equal to 2, this is f of x2 minus f of x1. And so it would be the next diagonal. And so in that way, you would get all the way up to the very top. Okay. All right. So keep this in mind. Keep this piece here in mind. Okay, so basically f of b minus f of a equals this sum. Okay, so keep that in mind. All right. Now, it's also true, okay, by the mean value theorem. So remember the mean value theorem. You may have to go back and refresh your memory with Calc 1, but go back and double check the mean value theorem. The mean value theorem says that there exists a CI, so a number, CI, between x of I minus 1 less than ci, less than or equal to ci, less than or equal to x of I. So within the ith interval, there's some ci, right, some number ci, such that f prime of ci is equal to f of xi minus f of xi minus 1 divided by x of I minus xi minus 1. So this is just again, you may have to pause the video, go double check what the mean value theorem says, but this is just a straight, nothing fancy here. This is just a straight interpretation of the mean value theorem. Between any two real numbers, if the function is continuous, there's going to exist another real number such that this relationship holds. Okay, so very good. Okay, so we've got this. So this is the mean. So remember, we've got this equation here. We've got this one here as well now. Okay, so let's hop over to the next page. Okay, and so something to notice here, a couple of little tidbits that are important. First of all, f prime of ci, what is that? Well, f is an antiderivative, big F is an antiderivative of little f, so when I differentiate big F, I get little f, right? Okay, so that's a fact. It's also fine to write xi minus xi minus 1 as your delta xi. That's just the change between xi and xi minus 1, so that's just notation. Okay, so let's take this previous equation and re-express it. So f prime of ci equaling this, that's going to imply that f prime of ci times xi minus xi minus 1 equals this difference. Shoot, I'm almost out of space. Okay. Here, let me write it again here. So it's equal to f of xi minus f of xi minus 1. So it's just this numerator piece here. Okay. Okay. All right. And so kind of combining this statement here with this previous fact, it's fine to write this as f of ci times delta xi, okay, xi minus 1 is just delta xi, f prime of ci is just f of ci, and to say that that is equal to your f of xi minus your f of xi minus 1, right? So again, just kind of re-expressing some of these things in different notation, right? Because they're equivalent, right? Nothing fancy yet, right? But it is, I mean, we are being clever. There's no two ways about that. Now, what happens if we sum over all of the i's here? All right, so let's just take this, I mean, because these indices are all valid from 1 to up to n, right? And so let's do that. Sum I equals 1 up to n of, I'm going to kind of switch the order here, like so. And that's going to be equal to the sum from I equals 1 up to n of this one. Okay. And over here, what we just saw on the previous, in the previous page, right, that what that's equal to, right? That's the sum of f of xi minus f of xi minus 1, right? That's this. Remember, that's our tricky little algebra section. That's all equal to this. So that can just be replaced by this. Okay, so over here I've got f of b minus f of a, and that's now equal to this sum. Okay, great. Okay. And so this equation really shows you that you can always find a collection of CIs, right, such that this is a constant, such that this constant f of b minus f of a is equal to some Riemann sum, right? So this is a Riemann sum, isn't it? Okay, so there's a Riemann, so for any constant, there's a Riemann sum. Okay, and well, what's the next thing? I mean, if we want to turn this into an integral, what do we have to do? We'll just take the limit as the partition, norm of the partition goes to 0 on both sides. Right over here, there's nothing to do, right? It's still going to be the same. If we increase the, decrease the width of the partition, that's going to just make this sum n larger, right? There's just going to be ever finer and finer, division of this partition. So, but it's still going to be the same quantity here. So nothing to do on this side, but over here we're going to get some changes, right? So let's write it out. So f of b minus f of a equals the limit as the norm of the partition goes to 0 of the sum I equals 1 to n of f of ci times delta xi. Right, now what happens here? What do we call this? Well, that's the definite integral, isn't it? So f of b minus f of a equals the integral from a up to b of f of x dx. And that's the result, right? That's what we're after. Okay, so letting this partition get finer and finer until the norm of the partition is 0, or approaching 0, arbitrarily close to 0, gets us to the definite integral. Okay, very good. So as I said, it's kind of I mean, for how profound this theorem is, it's relatively straightforward. There's some definite, nice tricks here, though, right? So this is a nice thing to notice. Obviously, the mean value theorem coming into play here is important. Some nice tricks, for sure. But it's not the kind of proof that is, totally elusive. If you understand the basic mechanisms of how we defined an integral, and you understand the idea of the norm of a partition going to 0 producing an integral, it's kind of a straightforward theorem and it's a straightforward proof. It really just kind of falls out, and it's very, very nice. As I said, one of my favorite theorems and one of the nicest proofs I've seen. Okay, so let's talk practical matters now. Let's talk practical matters. So let's make some notes. A few notes. Okay, so we'll talk a little bit about what this means, practically speaking, this fundamental theorem of calculus. So the first thing that it means is that indefinite integration and definite integration are very similar to items, right? They have a connection now. If you can find an antiderivative of f, so if you can find an antiderivative of little f, you can use the fundamental theorem to evaluate a definite integral. Okay. Right, that's basically what it's saying. So, the integral from a to b of f of x dx. Now, previously we would, up until now, what we've done is we've had to identify a CI, formula for the CIs, a formula, some kind of a value for the delta XIs, and then we'd have to, plug all of that into the function little f, and we'd have to take the limit as the, norm of the partition goes to 0 and figure out what this definite integral evaluates to, which is obviously extremely cumbersome. Right? This is how we've had to do it in the past. Well, up until this point. But what the fundamental theorem of calculus says is, well, look, if you can find a big f, an antiderivative of this function f, then it's really just a matter of taking that antiderivative and evaluating the upper and lower limits. It's really just this. This is much easier than this in almost every case. Right, assuming that an antiderivative exists, right? So what this basically means is that we can use the rules that we've been developing, the principles that we've been developing for indefinite integration, and we can now apply them directly to definite integration, right? So let's see an example, and this will be the second issue, the notational issue. So how do we notate this as we're doing it? So let's do a simple example. So say we want to evaluate the integral from 1 to 3 of x cubed dx. Right? So again, previously we would have to have gone through this method here, where we figure out what a CI is, we plug that in, cube it, and then we figure out what delta xi is, which is basically the bounds divided by n. So we would have been able to do it, but it would have been like a little bit of a lengthy process. But we do know, if we think of this as an indefinite integral, we have a nice, concise formula for how to identify the general family of antiderivatives of x cubed. We know that they are all of the form x to the 4th over 4. Now we're going to leave off the plus c for now, and we'll get to that in a second. Let's pretend there's no plus c here. So generally the antiderivative would be x to the 4th over 4 plus some constant. Leave off the c for now. We'll talk about it in a second. But now what we can do is we can just find the antiderivative and then plug in the values here, 1 to 3, right? And so this is the notation that people will frequently use. They'll put this in parentheses here and then have some kind of a vertical bar with the upper limit and the lower limit. So this is just telling you that you need to evaluate this at 3 and then separately at 1 and identify the difference. And so we could do that. We could just take 3 to the 4th over 4 minus 1 to the 4th over 4, like so. And you would get 81 over 4 minus 1 over 4. And so that's 80 over 4, which is 20. And so that quickly we can figure out this definite integral, right? Really quickly. Okay. So the notation here is kind of the key, right? So if your integral is from a to b of f of x dx, then the way to notate this as you move through the calculation is to say, okay, I found my antiderivative, and it's going to be evaluated from a up to b, and then I'm going to plug in those actual quantities and do the subtraction, right? And that gets you to your answer. Okay. So what about this constant? Because when we were talking about indefinite integrals, I was harping on the importance of the constant, and it is important in an indefinite integral. But in a definite integral, what happens to the constant? Let's see quick. So in the case of the definite integral, what about the constant? of integration. What about the constant of integration? What do we have to, what happens there? Do we have to worry about it? And if we don't, why don't we? Well, let's go through it. A to b of f of x dx, again, same notation as above. This time, let's put the constant in there. Right, it looks like that. And then what am I going to do? I'm going to say f of b plus c minus f of a plus c. And so what do I get? I get f of b plus c minus f of a minus c. So of course you can see what's happening here. F of b minus f of a plus c minus c, right? So there it is. The constants basically wash out. Okay, so you don't have to worry about it. All right. Very good. So basically with a definite integral, you can just kind of omit the constant of integration from your calculation. There's nothing wrong with writing plus c and subtracting it out each time. It's totally fine. But it's a little redundant, right? So you don't actually have to do that. Okay. Excellent. Let's take a look at some examples here and see how nice this is. Let's evaluate the integral from 1 to 2 of x squared minus 3. Okay, so again, this is, you're going to have this is a quadratic equation. There's going to be a parabola in the plane with the vertex of the parabola at y equals -3. And we're looking for the area between 1 and 2 on that between the x-axis and that function. And so this is the answer to this question is a number. And so how do we find that number? Normally we would have to we'd have to identify a candidate for CI, identify a partition delta x, and the width of the partitions would have to be identified, set up a sum, let the limit of as the norm of the partition goes to 0, evaluate that, blah blah blah, and a number would pop out. So, but now what we can do is we can just take the integral, and because this is just a polynomial, we know what the general form of the antiderivative of a quadratic equation looks like. We can just jump right to that and say this would be x to the 3rd power over 3 minus 3x. And that is going to be from 1 up to 2. There's the integration part of it. Okay, and then all we have to do is plug in our values. So this would be 2 cubed. I'm going to write it just because we're learning, right? We want to make sure that we're... Okay, so here I evaluate the antiderivative at the upper bound 2, and then I subtract from that the antiderivative evaluated at the lower bound. Right, it looks like that. And so you get 8/3 minus 6 minus 1/3 minus 3. Okay, and then all of this can be figured out. This is 8/3 minus 18/3, and then minus 1/3, and then be plus 9/3, right? So all together, what do we get here? We get 8 minus 18 get you -10, and then these two are 8 together, so you get -2/3 all together, right? So that's the value of this definite integral is -2/3. All right. So yeah, obviously much more straightforward, much more just like computationally direct than having to go through the definition. And I kind of liken this whole thing to, basically when we first learned derivatives, how to calculate derivatives, we had to rely on the definition of the derivative. And instructors intentionally make you do that for a week or two, just so that you get that idea in your head. And then abruptly we start figuring out faster ways to do things. Similar here, right? We started by calculating these definite integrals using the definition, which is a little bit obtuse as far as methods go. But it's important because that's really what's happening in the background. It's important that students kind of get used to it. But then we're going to switch to using antiderivatives to do these evaluations. It's much more efficient. Okay, let's do some more examples here. Let's evaluate from 1 to 4, 3 times the square root of x. Okay. So similarly here, I'm going to pull out the constant, and then this is just basically x to the power 1/2, which we can quickly evaluate. So this would be equal to 3 times, so this would be x to the 3/2 over 3/2, evaluated from 1 up to 4, right? That's the general form of the antiderivative, that with a constant. And so we can do this math really quickly. Actually, let me do a little bit of, so this would be 2x to the 3/2 over 3. Let's do a little simplification before we, so this would be basically 2x to the 3/2 power from 1 up to 4. And what do we get? We get 2, and then it's 4 to the 3/2 minus 2 times 1 to the 3/2. Okay, and I'll just leave it to you guys to figure out what that number is. It's like, 4 cubed square root of that, 1 cubed square root of that. Subtract those two and multiply everything by 2. So you're going to get some answer. I don't have it in front of me, but there you go. But still like very straightforward. This fact that we know the antiderivative of the square root of x makes solving this problem very quick and very easy. Okay, but no less remarkable, right? We're still doing a remarkable thing. It's just we figured out that there are easier ways to do this remarkable thing. Okay, how about another example? Here we'll look at the integral from 0 to 2 of the absolute value of 2x minus 1. And what does this one look like? Let's draw it quick. So xy axis. So if this is 1, 2, 3, and then we'll put this as 1, 2, 3. Then this guy kind of comes down like this. It has, a little bit of a steeper slope. And then it kind of looks like that. And so we're interested in the area here. All right, so kind of these two parts, aren't we? All right, that's what the absolute value function looks like. So this is an example. Whenever you have these absolute value examples, it may be possible to break it up into two pieces that don't involve an absolute value, and that's what we're going to do here. So we're going to rewrite this function. Okay, and so if you take the time and you say 2x minus 1 equals 0, you can see that x equals 1/2, and so that's sort of where we have to be. That's sort of the boundary where the absolute value sort of takes a different character, right? So if x is less than 1/2, like i.e. this line over here, this is just a line, right? A linear equation, a linear function here. And so you can see that the slope would be -2, the intercept is 1. So you could write this as -2x plus 1, and that's when x is less than 1/2. And then after x equals 1/2, it's kind of the reverse, right? The intercept would be down here at -1, which I haven't drawn on here, but you can picture that. And the slope would be 2, right? So basically it would look like this. Okay, and it doesn't matter if you make this inclusive of 1/2 or this inclusive of 1/2, whichever is the same. When we're talking about integration, that detail doesn't matter. Okay, so you can set it up like this, and so then we can use this nice property of definite integrals where we can break the range of the integration into two pieces, or however many pieces. In this case, just two. So we'll go from 0 to 1/2, and over that interval, the function looks like this: negative 2x plus 1. And we're going to add to that the upper section from 1/2 up to 2, and over that interval, it's 2x minus 1. Okay, so it looks like that. And so these are straightforward polynomials, there's an antiderivative for that we know. And so let's write it out. So this would be negative 2x squared over 2 plus x, and that's from 0 up to 1/2. And we're going to add to that, looks pretty close, just not negative, right? So it'd be 2x squared over 2 minus x, and that's from 1/2 up to 2. Okay, so there's the two antiderivatives. Let's clean it up a little bit before we do the actual plugging in here. Okay, like so. And let's see here. So we got to be careful here to make sure we follow what we're doing. We're going to figure this out at 1/2, and we're going to subtract from that the same thing at 0, and then we're going to add to that the same practice with this lower section here, this other section. So what do I have? I've got negative 1/4 plus 1/2. Okay, and I'm going to take that and I'm going to subtract from it negative 0 plus 0, so just 0. I'm going to write it in here just so that people can, because sometimes it helps to see like what part went where and where did things go. So for when you're learning, you always want to just like err on the side of more steps than necessary. And so here it'll be 2 squared, so it'll be 4 minus 2, and then minus, and evaluate the whole thing at 1/2, so it'll be 1/4 minus 1/2. Okay, so it looks like that. All right. And we can figure this one out. Let's see. So it's negative 1/4 plus 2/4 here. And that's just 0, so we're not going to worry about that. Then over here I've got 4 minus 2, which is 2. And then minus 1/4 minus 2/4. Okay, so up here I've got 1/4 plus 2, and then this will be 1/4 minus 2/4, so minus 1/4, but it'll actually end up being plus, so plus another 1/4. Okay, and so this would be like 2.5, otherwise known as, I think, better written as 5/2. Okay, so there you get to the 5/2. Okay, very good. So that's a good example. Right, obviously this one would be very tricky, right, if you had to use the definition. All of these would be tricky using the definition. Just because there's a lot of bookkeeping, right? A lot of CIs and delta XIs and da-da-da. And it's somewhat, obviously, much more straightforward if you can just use the antiderivative to calculate the definite integral. Here's another example. The integral from 1 up to e of 1 over x dx. Okay, this is, 1 over x. We know that there is an antiderivative for that. It's the natural log of x. And so evaluating that from 1 up to e is just as simple as ln of e minus ln of 1, which equals, of course, 1 minus 0, which is 1. Okay, one-liner there. Okay, very good. So there's a bunch of examples of the fundamental theorem of calculus in action. All right, so now let's take a look at, we're going to not totally shift gears, but we're going to develop another theorem, and then we'll use that as well with the we're going to develop another theorem that we'll use to talk through what's called the second fundamental theorem of calculus. Okay, and so this is going to be what's called the mean value theorem for integrals. Okay, and so previously we had talked about, if you have a curve, I'm going to try to draw the same curve 3 times. Okay, so there's different ways to do it, right? You can use, the upper sum. You could use the lower sum. Right? In the case of the upper sum, you get too much area. In the case of lower sum, you get, you're missing a piece. And so the truth is kind of the middle, right? Obviously, it's between those two. It's sandwiched between those two. And so the mean value theorem is going to state this sort of truth a little more precisely. Okay. So here it is. Let f be continuous on AB. Okay. Then there exists some number C in AB. Okay, such that the integral from a up to b of f of x dx is equal to f of c times b minus a. Okay, so this is the the mean value theorem for integrals. So what does this mean? Let's draw a picture, because I think motivating like what this is describing can be really helpful, right? So let's try to draw a nice, so I've got some function here, and I've tried to make it look a certain way. So let's say this is a down here and this is b up here. So there's some area underneath a and b, right? Which I can kind of loosely shade in that way. Now, what this is saying is that there's going to be some c in here, and I'm going to eyeball it. It's probably right about there. It doesn't have to be necessarily in the middle. In this case, it does happen to be in the middle. If there's going to be some c such that f of c, which would be kind of like right about here, right? Such that the area swept out by f of c times b minus a is equal to the area under the curve, right? And so you can imagine, f of c is kind of like this. There's some area in that rectangle which is going to correspond precisely to the area under the curve over the entire interval. Okay, so the area inside this rectangle okay, there's some area swept out there. You can see I drew it on the picture, but it's just a rectangle, isn't it? It's f of c high and b minus a wide. You multiply those two together, you get an area of a rectangle. And that c is going to be somewhere between a and b, and it's going to, the area underneath that, constant line f of c is going to equal the area under the curve. Okay, so it's kind of like the average value. Okay, that's why it's called the mean value theorem for integrals. Okay, so very good. Let's prove this theorem. I actually really like the proof of this one as well. This is a good day for Calculus 2 proofs. So let's prove this mean value theorem. Let's take two cases, right? Case one will be the straightforward case where f is some constant function. Well, if f is a constant function, then basically the area is already equal to the rectangle f of c times b minus a, right? Right. If f is a constant function, then basically any c in the interval a to b works. right, gives you the same area as the area under the constant function f, right? Hopefully that's kind of obvious. Okay, so let's look at the other case. Case 2, we'll assume f is not a constant function. Okay, and by making this assumption, we can introduce other little facts, right, from all over the world of mathematics. So, in particular, if f is not constant on AB, then there's going to be some little m and a big M, right, in the interval AB. Okay, there's going to be some little m and a big M in AB, such that what? F of little m is the min, and f of big M is the max, okay, on the interval AB. Okay, and now just to restate that, what does that mean? Well, that just means that little f of little m will be less than or equal to f of x, which will in turn be less than or equal to f of big M. And this will be for all x in the interval AB. Okay, this is the min value, this is the max value. That's all that means, and everything else in the interval is between those two. Okay. All right, so nothing controversial in that, right? F is a non-constant function. It's going to have a min and a max. Even if it was a constant function, it'd still have a min and max. They'd all just be the same value. But there's nothing controversial here. Okay. Now let's integrate this. Let's integrate each piece of this, from a to b, right? So we'll take the integral from a to b of f of m, little m. That's going to be less than or equal to the integral from a to b of f of x. I should be putting my dx's on here, of course. And that's going to be less than or equal to the integral from a to b of f of big M. Okay. Right, so we know from previous sections that integration preserves inequality. Right, all of those inequality relations hold and are preserved under integration. Okay, now something important to notice here is that these are constants, right? Right, f of little m is a number, right? Just we don't know what, in general we don't know what m is, but there's some m number, and when I evaluate f of little m, I get a number. Right, so this is a constant, this is a constant, this is not a constant. F of x is a function of x, right? X is a variable. So, but this is basically just the integral of a constant. Okay, so we can figure that out really quickly. It's just f of m times f of, well, since it's a constant, it's actually just evaluates to x, right? So then you'd have f of big M. It's a constant, so you can pull it out. And again, it's just x. Okay, so it looks like that. And we can easily, so all of this is implication, right? This implies that, implies. And so this would just be little f of little m times what happens here. It's going to be b, evaluate x at the top, minus evaluate x at the bottom. So it looks like that. Great. Okay, so we've got that. Okay, and of course then we can divide everything by b minus a, and so I've got some constant here that is basically f evaluated at little m. That's going to be less than or equal to 1 over b minus a times this integral here, which would be less than or equal to f of big M. Okay. All right. Now, the intermediate value theorem is going to guarantee that there exists some C in the closed interval a to b, such that, right? So again, intermediate value theorem. Got to go back and check what that is. Intermediate value theorem says that there's going to be some C in AB such that f of C is equal to 1 over b minus a times the integral from a to b f of x dx. Okay, now, okay, hold on. So look, what happened here? Well, I've got the minimum on the interval is f of little m. The max, so let's write that min, max, right? So this is a continuous function, so I've got the minimum value, I got the maximum value. In between, there's going to be this, whatever this is equal to, which we're going to call f of c, right? We can do that. We know that there's some c in there that's going to equal whatever this number happens to be, since it's a continuous function, and this is between these two this minimum and this maximum. That's just all the intermediate value theorem tells us, right? And so this being the case, then this gets us to basically to our situation, right? We want to multiply both sides by b minus a now. And so f of c times b minus a is going to be equal to the integral of f of x evaluated, the definite integral from a to b of f of x. Right, so this is this was kind of our target. We wanted to drive this. Okay, so a beautiful proof. Very, I mean, it's super intuitive, right? You can't. There's no part of this that requires an enormous logical leap. Hopefully, right? You start with case one is uninteresting. Case two, f is non-constant. There's going to be some little m and some big M on that interval, such that f evaluated at those two values gives you the min and the max respectively. Okay, and from that, this is just the implication of this being a min, this being a max. You have this. Okay, integration preserves inequality, so you can integrate all three pieces here. Notice this is a constant, that's a constant, so the definite integral is basically going to be the constant times b minus a, and again on the upper side it's the constant times b minus a, so this is sandwiched between these two constants. Okay. Intermediate value theorem says this is a number and there's guaranteed to be some c that equals this number, right? It's between these two values. There's going to be some c which, when I evaluate the function, is going to give me this number. And so that being the case, you get this f of c is equal to that, and then it's just algebra, multiply both sides by b minus a. Done. Okay. Very nice, slick proof. Okay. So then, what is this mean value theorem for integrals? What is the significance? Well, this mean value theorem is actually, this mean value that we pointed out is actually going to tell, this f of c is going to give you the average value of a function over an interval. So basically the value given by f of c, from the mean value theorem, is called the average value. Of the function over the interval, right? So let's actually use that as we'll define this here. So definition: if f is integrable on AB, then the average value of f on the interval is 1 over b minus a times the integral from a to b of f of x dx. Okay, let's this is a definition, so we're not going to there's no, you don't have to prove definitions. Definitions are just definitions. But let's talk about like why this works. What is this? How is this so? So as we so often do, let's start with the partition of AB. Okay, and we'll partition it into n subintervals. So into n subintervals. And so then basically delta x would have a width of b minus a over n, right? So I guess we could write that. So a equals x0 less than x1 less than x2 dot 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 less than xn equals b. Okay, so then if ci is any point in the ith interval, say delta xi, and we'll just write that out, x of I minus 1 up to, well, so actually it's a difference, minus x of I, right? So if ci is any point in the xith interval, which would be kind of defined by this piece here, then the arithmetic mean of the function values at the CIs would be given by the following. So imagine a CI in each one of these intervals. So one here, here, all the way up. So there's n of them. What's the average function, average value of those CIs evaluated in the function, right? So basically you would take f of c1 plus f of c2 plus dot 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 f of cn. Okay, so just add them all up. How many of them are there? Well, there's n of them, divide by n, and so we're going to call that the arithmetic, sort of the arithmetic mean. Right, this is the average. This is just the average. Right? So there's a bunch of CI values. What's the average of them? This is it. Okay, and so let's write that like this. Just moving the n out front here, the 1 over n. And so then, of course, that's equal to the sum 1 over n times the sum of f of ci, I equals 1 up to n. Okay. And so that's all. Nothing there is controversial, right? No controversy there. This is just a sum, it's an average, basically, of some arbitrarily chosen CIs in each of the xi intervals. Let's do some algebra tricks now. So a sub n equals 1 over n, I equals 1 to n of f of ci. Now let's multiply and divide this by b minus a. We can do that, right? That's just multiplying by 1, no problem. But we know that this is an algebra trick that we're about to perform here. So we're going to take the denominator, pull it outside of the sum, and we're going to bring this n back in. And so when we do that, we get this. Okay, and we know, of course, this b minus a over n is the width of the intervals. So I get now technically these delta xi's are all the same, so I could just rewrite this as, it doesn't really matter actually for this derivation, but I'll do it just because I said it. So it's technically just delta x. Now, this is a Riemann sum, right? This is a Riemann sum. So whenever we see a Riemann sum, it's a quick step to get an integral. What do? Well, we either let the norm of the partition go to 0, or equivalently, we can let the we can take the limit as n goes to infinity, right? So either way. So either way, doing that, we'll just say letting delta go to 0 or n go to infinity, same thing. That gets us to what we're looking for, which is that a of n is equal to the sum, is equal to the integral a to b of f of x dx. Okay. Oh, sorry, 1 over b minus a. That's there too. Sorry. Yeah, this part here. Can't forget that part. That's b minus a. Okay. Okay, and that's basically the definition, right? So it says the average is just, you know, has this form. Very nice. Okay. So let's do a quick example of this. Let's find the average value of a function. Find the average value of f of x equals 3x squared minus 2x on the interval 1 to 4. Okay, so we know that the average has the form 1 over b minus a times the integral a to b of f of x dx. So it's just a matter of like plugging those values in. 1 over 4 minus 1 times the integral from 1 up to 4 of 3x squared minus 2x dx, like so. So that's 1/3, and then this integral would be 3 times x cubed over 3, so just x cubed, and this would be minus, and then minus 2x squared over 2, so just x squared. And 4 times 4 is 16, times 4 is 64, minus 4 times 4 is 16, and then minus 1 minus 1, basically. Okay, and so what do we get? We get 1/3 times 64 minus 16, which is 48. And so that is 16. So the average value of this quadratic function on this interval is 16. Now this is, I think, you know, can be more useful than you might initially think, right? This, in the case of a function that's really symmetric on the interval, like it's kind of obvious what the average value might be. But in the case of a function like this, which is not at all symmetric on this particular interval, then it's not obvious why this would be the case, right? Or this value is not obvious. So this integral gives us a lot of capabilities. Okay. All right. So there's more to say in this lecture, but I'm going to break the video into 2 pieces just to save on time. So we'll come right back and jump into the setup for the second fundamental theorem of calculus.